Okay, we might get started. So thanks everyone for coming to today's signature lecture of the ARC Center of Excellence for Enabling Eco-Efficient Beneficiation of Minerals. I also like to start with the acknowledgement of country and acknowledge the traditional custodians of country throughout Australia, their connections to land, sea, and community, and pay our respects to their elders past, present, and emerging. And I extend that respect to all Aboriginal and Torres Strait Islanders people today all over the country and where we're coming from different states as well, etc. And so today we're lucky enough to have Aleksandar Nikoloski as our signature lecturer from Murdoch University. Aleks is the director of extractive metallurgy at the Harry Buttler Institute, and I've worked with him about the last 5 years as he was the project leader of lithium project in future battery industries, and now he's a program leader in the CRC for critical metals for critical industries. And Aleks is going to tell us about his work in extractive metallurgy today. So, thank you.
Thank you very much, George, for that warm introduction. Thanks, colleagues, for participating in this lecture. I'm very honored to be presenting to you and talking about extractive metallurgy. So I've always had a strong admiration for University of Melbourne, and Melbourne is the first city that I landed in when I started my journey in Australia. So I'm very pleased to have this opportunity. My talk today will address the subject of extractive metallurgy as a catalyst for innovation to a greener future. And I'll start with a short introduction of why extractive metallurgy matters in this day and age. And then I'll follow some examples of achievements that we've had in this field at Murdoch University and together with our colleagues, collaborating partners from other universities, including University of Melbourne. And then I'll tell you briefly about the Extractive Metallurgy Hub, which is a specialized facility at Murdoch University that we've opened last year. Tomorrow is our first year anniversary, and what it does, why it matters, and how we hope to progress further, especially involving collaboration with colleagues from other institutions. So the simple point is that modern high technology devices and clean energy depend on metals. And lithium has been very widely publicized lately because of its use in lithium-ion batteries, but it's not just lithium. Obviously, there is nickel, cobalt, copper, rare earths are very important these days. And we will need a lot more of those.
Aleks, you're still on acknowledgement of country slide.
Oh.
It hasn't progressed.
Let's see why that is. What about now?
Still says acknowledgement of country.
Is that better?
Yeah, now you're in extractive metallurgy. Yeah.
Okay.
Thank you.
Okay. Is the change working now? Am I back to acknowledgement of country?
No, it's on extractive metallurgy.
Okay.
Brief introduction.
I don't know why that doesn't work, but yeah. So I'll start with a brief introduction of extractive metallurgy and the Extractive Metallurgy Hub, and then I'll tell you a little bit more about the achievements. So the Extractive Metallurgy Hub was opened in July last year to drive the WA transition to sustainable minerals production. It is very important for Western Australia because it helps us progress from being only a supplier of resources to being a leader in clean energy metals production. It brings together research capability, specialized facilities, and industry facing expertise with support from the Mineral Research Institute of Western Australia and the state government, we were able to open up this new facility. So the work that we do is under the Harry Buttler Institute, which is responsible for sustainable living development initiatives. And I'm responsible for leading the research and workforce development efforts in this space. Clean energy transition increases the need for metals, we know that, but society expects them to be produced in ways that lower the impact and with greater circularity. So when people think about clean energy, they often associate it with solar panels, wind turbines, electric vehicles, and batteries. But sometimes the fact that all of those technologies are produced from largely metals is forgotten. So it's essential that we inform society and develop technologies for production of metals, but in a smarter way, in a way which is cleaner, more resilient, and circular and trusted by the communities. So our work contributes in three main ways. Firstly, by providing cleaner supply of critical metals, extracting more value with less waste and lower emissions. Secondly, by ensuring circularity of metals, recovering the elements from the end-of-life devices and residues. And thirdly, by sharing prosperity, building sovereign capability and industry partnerships and skills. So for a non-technical audience, the takeaway of this would be simple, that we design better ways to extract, refine, and reuse metals that society already depends on, and making sure that the community understands that. So what does that work look like day to day? The clean energy transition increases the need for metals, but society expects them to be produced with lower impact and greater circularity. There is a lot of discussion about this these days. We have regular meetings with the Mineral Industry Research Institute of Western Australia about how to ensure that circularity occurs. When people think about clean energy, they often appreciate that, but they fail to understand that those metals are mined, and everything basically is mined. Extractive metallurgy turns those complex resources, which are available in a form which is not ready for application in devices, into materials that are suitable for building of those devices. The materials that we need do not usually come out of the ground ready to use, and we need to transform them by removing the impurities through dissolution in solutions or the smelting to convert them into the materials that are required for those devices. Batteries are a good example. The hub focuses on the steps that turn those complex inputs into useful materials by separating, purifying, and making the required products, and where possible, recycling them. So the useful phrase is selective chemistry. We want the metal we need to move into the right products while controlling the impurities, reagents, and water residues. And that is what makes that work practical for industry. It's not just about recovering the metals, it is about doing it reliably, safely, and at the scale that can be commercially adopted. There are three practical ways that the hub that we've got at Murdoch University creates this impact. First is by smarter chemistry. Hydrometallurgical processes can be tuned to recover target metals more selectively and regenerate useful reagents. Second is by recycling and circular supply. Spent batteries are a significant focus area for us, and residues from mining. Other urban mine materials can also become new sources of critical metals. Third is the scale up and skills. Bench and pilot facilities are available at the Extractive Metallurgy Hub that help validate some of the technologies that we have developed on the bench scale into pilot plant operations, which generate larger quantities of product, which can be characterized and provide evidence of the reliability of that new technology, but at the same time provide an opportunity to train the workforce, train engineers who can take those processing solutions to commercialization. So the headline message of this is that the future is not metals-free, it is metal-smart, and extractive metallurgy is the bridge between the critical resources and the clean energy, circular manufacturing, and advanced industry systems that we want. This brings me to the next part of this presentation, where I will focus specifically on the utility of extractive metallurgy in powering a cleaner, smarter, and more sustainable future. Clean future, as I said, needs more metals. And those metals are the majority of the elements in the periodic system. Sometimes we need to explain to students in high schools when they choose their careers for their future that out of the 118 elements in the periodic system, 95 are metals or metalloids. So if we consider the type of industry that we have in Australia, which is predominantly mineral resources driven, this is a major opportunity for our students to establish a rewarding career. The metals are durable at the same time. They're basically indestructible. They've been here long before we arrived on this earth, and they will probably stay here forever unless they decay radioactively. And that provides the opportunity to ensure sustainability, a circular economy where they can indefinitely use those resources. I therefore would like to mention that the metals matter, and the energy transition has created critical metals, critical minerals challenge. Until 5 years ago, we didn't even use the term critical metals because it is a concept that has evolved rapidly with the need of those ingredients for powering high-tech devices. And the significant opportunity for advancement we see specifically, for example, in hydrometallurgy. The demand is very clear. Growth in battery metals is being driven by electric vehicles, batteries, and renewable energy and grid infrastructure. According to the IEA, about 85% of the recent battery metal demand growth has come from the energy sector. Lithium has grown in demand 30% in 2024, while the demand for nickel, cobalt, graphite, and rare earths has also shown strong growth. This is not just a mining story, therefore, it is a processing story. And higher demand means we need more reliable ways to extract, separate, and purify and recycle those metals. Lithium is essential in this discussion because it helps illustrate the base of change very nicely. The global lithium mine production has reached around 240,000 in 2024, which is roughly 150% above the 2018 levels. And this increase is essential for batteries, but it also creates pressure on energy use, water reagents and residues, and product quality and community expectations. The message is that we don't just need to mine more, we need to process better. We need high recovery, lower waste, more selective chemistry and circular approaches that brings those batteries, the end-of-life materials, back into the system. The research that we have done as part of the development of this lithium technology in recent years shows that there are significant opportunities for improvement. The metals, as indicated, rarely arrive in the form that we need for industrial applications. They typically begin as complex ores, brines, concentrates, and extractive metallurgists create the value through separation, conversion, purification, and recovery that turns this variable resource into a reliable material that meets specifications for fabrication of devices. That bridge matters because clean technologies depend not just on the metal tons, but on the purity, consistency, traceability, and the ability to scale production safely. Future supply of those resources will not come only from simple high-grade resources. Grades are falling in many systems, and impurity profiles are more challenging. So projects face much greater scrutiny around water, reagent, residues, and social license. This changes the role of the metallurgist. We're no longer just maximizing recovery, we're designing processes that balance recovery, selectivity, emissions, water use, residual waste, and quality of that material, which potentially could turn it into a new secondary resource. So in other words, the processing route becomes a sustainability decision. We find that increasingly processing plant managers are more concerned about the legacy that they will leave behind than about the total throughput or profit that they will achieve during their tenure. Spodumene is an important element to mention in this discussion. It is an important source of lithium, but it is not straightforward to process. Conventional processing typically requires high temperature calcination at about 1100 degrees Celsius to transform the original mineral, which is in an alpha spodumene form, into a more leachable phase, beta spodumene, from which we can extract the lithium by acid baking and purification. This is a process that has been developed a long time ago, in the 1940s. It works, but it's energy intensive and can be very restrictive in terms of the feed that it can accept. It's not suitable for processing of fines, for example. And it also has limited tolerance to impurities. And it generates aluminosilicate residues, which typically contain sulfate, a lot of sulfate, which limits its utility for downstream use in construction applications, for example. So this is something that we identified as an opportunity for improvement and innovation. So it became clear that we need to rethink how this flow sheet operates completely, starting from end to end, reducing thermal intensity where possible, improving selectivity in the recovery, managing impurities earlier in the flow sheet, and finding value or safer pathways for the residues. The broader lesson from that research was that cleaner production is possible, but it starts by redesigning all of the unit operations, not just adding a fix at the very end where we look at what to do with the residue. This is illustrated by this slide where we see the flow sheet, the typical flow sheet for a conventional lithium refinery, where we identified several areas for significant improvement opportunity, starting from the mine, where the more complex ores, which have more impurities or finer grade particles, were not suitable for commercial processing. Significant energy was consumed in the grinding. There was limited ability to recover the fines by flotation. A lot of energy consumed in the conventional calcination and acid roasting process, and also the fact that we have acid in the system, which led to sulfate in the residue and dissolution of the gangue minerals. There was also perceived inefficiency in the neutralization of the slurry after the acid treatment, which led to significant consumption of neutralizing agents, and then inefficiencies in the recovery of the lithium in the final stages, which could be improved by improving the precipitation or adopting electrodialysis as an alternative approach to recovering the lithium. In this area, we were able to make some significant improvements. A major opportunity was to treat the waste stream as a source for additional sulfuric acid and caustic using electrodialysis. The electrodialysis requires a membrane for separation of the elements from the solution stream, recovering in the case of sodium sulfate, sulfuric acid, and caustic, or in the case of lithium sulfate, lithium hydroxide, directly without the use of solid reagents for precipitation. It became clear that this is a significant opportunity, but it also is not straightforward, and impurities, for example, significantly impact on the effectiveness of the process and ability to have a sustained smooth operation. So the aim was not just to produce a cleaner product, but also clean up the system, make sure that impurities are removed before the electrodialysis stage, and ensure that the membranes can be appropriately managed. Cleaner production depends on those processing solutions, but it also depends very much on the ability to incorporate intelligent controls into those. This means rapid characterization of the ores, utilizing effective characterization tools. The residues, the black mass, in the case of recycling of batteries, models that link the mineralogy, chemistry, and energy, and control strategies that adjust comminution, extraction, and purification in real time. So the point is that digital control tools are a significant opportunity and help metallurgists improve the ability to adjust for the variability in the feed. The urban mining concept was something that became very popular lately. Recycling is indispensable for critical mineral security, but it needs to complement mining rather than replace it. We find that the recycling of lithium-ion batteries, for example, is not very effectively done in Australia. Less than 10% of the total disposed batteries are reaching recycling plants, which is very different to, for example, lead-acid batteries. It is understandable that it's harder to effectively collect and sort lithium-ion batteries, seeing that they come in very many different chemistries and they're much smaller. So collecting them from the community involves some behavioral changes. We've seen, for example, in other types of batteries, such as lead-acid batteries, historically, much better recycling efficiency. But their chemistry is relatively standard compared to the still rapidly evolving lithium-ion battery chemistries. I find this a topic that's very close to heart because my first research project as a chemical engineering student more than 30 years ago was actually recycling of lead-acid batteries. So I find it quite satisfying to work on recycling batteries these days as well. Hydrometallurgy gives spent batteries a second productive life. We started working on recycling lithium-ion batteries about 12 years ago, I think, at my group. We initially focused on the conventional approach of looking at the battery as in a similar way to which we would look at a rock metal source. We considered how you might be able to liberate the different components, concentrate them, and then treat them separately as concentrates. It became clear that the black mass is where most of the value is located, and that extracting the elements from that black mass is relatively straightforward from a chemical point of view. The real issues became the safe way of processing those batteries, which starts from the collection point, because a lot of incidents with fires and explosions occur due to the residual charge in those batteries. So we focused on developing discharging technologies, making sure that we can safely process the batteries downstream, transport them even from one location to another. A lot of research was then done to make sure that the extraction is done with the most benign systems. Lithium is a relatively soluble element, so it's not necessary to use a very intensive process. And we had good success in that. The black mass processing is chemistry under real world conditions. So the breakthrough that we see required was minimizing the hazards, lowering the reagent toxicity, and generating cleaner products. So once we realized that lithium is relatively easy to solubilize in various systems, hydrometallurgical systems, the first ones that we focused on were hydrochloric, sulfuric acid, and other inorganic acids. We started focusing on more benign systems, and we had a breakthrough in finding that, for example, vinegar and sugar as a reductant rather than hydrogen peroxide provided similar extraction efficiencies. And these are systems which the community finds very attractive, obviously. Binder removal was another aspect that we found could be optimized because it is a coating that potentially prevents the penetration of reagent to the elements of interest. So we considered different ways of removing that binder, either chemically or pyrometallurgically, for example. This was quite successful. However, we still see relatively little adoption of the chemical processing in Australia. Most of the material is still processed overseas. The risk involved is primarily in the availability of sufficient materials for processing, scaling up the process, and the varied chemistry of those batteries. Obviously, for a recycling business to be successful, there needs to be some product that can be generated and sold. And with the reduction of cobalt, for example, and nickel in those batteries, the value of that material has also been decreasing. So we constantly have to adapt the chemistry to make sure that we get reasonable outcomes. Another significant advancement has been incorporating low carbon metal processing options. We need to consider options to electrify recovery, reduce heat intensity, use cleaner reductants, and close utilities. A cleaner flow sheet turns byproducts into a design question. Waste is expensive. Useful residues that could be applied in other sectors are becoming very important. If you consider that a typical plant producing metals is usually targeting a few percent at best of the content of the feed material that enters that plant, you realize that more than 95% of the product of that plant is material which is currently considered waste. So making sure from the onset that the process design involves circularity and the utility of all the streams is essentially important. We also find that a significant gap exists in the scale-up of those technologies. What we typically focus on is the bench scale test work, but for technology to be pliable on a commercial scale, typically you need to demonstrate its efficiency on a continuous integrated power plant scale. And the infrastructure for those scale-up applications is relatively limited, not only in WA, but across Australia. The advantage moves from who has the ore to who has the ability to process that ore cleanly, intelligently, and at scale. At the moment, we find that majority of the processing that occurs in Australia is focused on the front end, the beneficiation. And a lot of those materials are then exported overseas for processing, from where they find applications in various sectors, such as electric vehicles, clean energy generation and storage, space and defense applications, and so on. We need to gain more ground further downstream in participating in those sectors. This is obviously of strategic importance for Australia, but also for our partners around the world who utilize those metals in various high-tech applications. The Extractive Metallurgy Hub has been participating in this field for many years very effectively, and we build on a long track record of research and education in extractive metallurgy. Last year, we had our 50th year anniversary of operating as an extractive metallurgy department at Murdoch University. And with the establishment of the Extractive Metallurgy Hub, we are now well placed to continue that contribution and engagement with industry for hopefully another 50 years. The Extractive Metallurgy Hub was launched, as I said, last year. It is run under my leadership. We have several senior people, including Dr. Tuma Isa, Professor Pritam Singh, who bring a lot of years of knowledge in research and education at academic level. We also have several adjunct colleagues who are senior people in the industry, including Dr. Angus McFarlane, Chris Ward, and Donny Bana, who was previously the head of metallurgy at Curtin University. We have several senior researchers, Dr. Rory Gilligan, Dr. Onya Sitando, Shane Wilson, who are mostly engaged in applied research. Also, Dr. Pan, Dr. Ang, and Mr. Gideon, who are some of our research fellows and research staff. And we have several PhD and master students. These are three of our current PhD students, Georgina, Joseph, and Kate. Georgina won the highest chemical engineering award in WA this year, so very proud to point that out. And both Georgina and Joseph will be participating in the Critical Metals conference, OSIMM conference in Brisbane later this year. So our focus is to develop cleaner technologies for production of critical metals, ensuring sustainability. The focus is on scalable technologies that can extract, process, and recycle critical metals, essential for battery technologies and metals production. And we try to accelerate innovation, strengthen Australia's sovereign capability, and train the next generation of metallurgists. Over the years, we have focused on research on various metals, some of which are listed on this cartoon slide: lithium, nickel, PGMs, cobalt, zinc, iron, uranium, thorium, rare earths. As I said, we have a long track record in this field, and we have been very focused on partnering effectively with industry, government, and other universities to help develop the solutions to many of those problems. Metals are, as I mentioned earlier, essentially indestructible and therefore infinitely recyclable. I think if we are successful in ensuring that circularity, making sure that the raw materials are effectively captured at the end of their lifetime, operating life, and brought back into the system, future generations will thank us for that rather than blame us for what we've done. We just need to make sure that this is appropriately incorporated into the future technology development so that we have a full cradle to grave, but also back to cradle approach rather than disposal. It is becoming clear to everyone in the community, I think, that sustainable value chain for clean energy storage solution is of benefit to everyone. And lithium is a very good example of that. It is not easy for the industry to operate in this space because of the various global volatilities and changes in the markets, but I think that the direction is clear to all. Chemical and metallurgical engineering graduates, on the other hand, have a major role to play in this. As I said, in Australia, we all understand that the mineral resources is a major sector, but sometimes we fail to understand and appreciate that we're mostly participating in the front end, in the exploration, geology, mining, and to some extent beneficiation. But processing those beneficiated materials to high purity ingredients for fabrication of high-tech devices is also what falls in our domain, and we need to make sure that we develop those technologies appropriately. Another significant component to this is the workforce. A critical requirement for any production of purified products from primary or secondary resources is the processing. And in Australia, this has been significantly reduced or diluted over the past 20, 30 years. We see a risk of major labor shortages, which is a major amplifier of all the risks to being able to produce metal sustainably in the future. Particular areas where shortages are seen is mineral processing, but also pyrometallurgy, hydrometallurgy, electrometallurgy, and overall plant design. It is very, very encouraging that lately the discussion on how to address those labor shortages is increasing and reaching all levels of community and government. We hope that we can participate effectively in the future supply of critical metals that requires investment in capital and technology development, but also investment in education of the future workforce. So at the Extractive Metallurgy Hub, we have established suitable laboratories and piloting facilities for development of processes that beneficiate, extract, and recover metals. We have specialized laboratories for characterization, handling radioactive materials, and electrochemical studies. So we basically can go from bench scale testing all the way to pile scale operation and optimization. Some of the equipment that we use at the hub is listed here. We have high pressure autoclaves, analytical equipment, which includes ICP, XRF, UAVs. We have XRD, STA, which is simultaneous thermal analysis, TGA, coupled with a DSC that can go to very high temperatures, and imaging and elemental analysis infrastructure such as STM-EDX. These are images of some of our hydrometallurgical power plants. On the one side is a leaching skid with a series of continuous stirred leach reactors. On the other side is an electrowinning power plant, which can handle full-scale anodes and cathodes. So this has also become part of a new CRC, which we call Critical Metals for Critical Industries. The Critical Metals for Critical Industries CRC is focusing on converting our mineral endowment into purified commodities for use in manufacturing sector, in developing industries for those critical metals. So we've identified several high targets or low-hanging fruits, if you like, which consists of lithium, vanadium, rare earths. Copper is also part of that. The idea is to ensure that we can refine the elements from those critical mineral deposits effectively to produce those metals so that they can be effectively utilized downstream and generate value. The potential target is very attractive. So here we can see the initial project pipeline that is envisaged as part of that Critical Metals for Critical Industries CRC, with vanadium, copper, lithium, and rare earths being some of the first opportunities that we will try to realize. We have joint projects or proposals at this stage that we're planning to launch with the University of Melbourne, and George and some of our other colleagues from University of Melbourne are helping ensure that we progress that effectively. This is a photo of the Extractive Metallurgy Hub building with myself and some of the researchers and the students working there. If you're ever in that area and able to visit us, please do so. We would love to see you. We'd love to meet you and give you a tour of the facility. We believe that critical metals are shaping the architecture of the 21st century, and it is our responsibility to build supply chains grounded in trust and fairness so that future generations inherit that legacy and they can thank us for that, as I said, rather than forgive us for it. So I think from this talk, it is clear that the future is not metal-free. We will need a lot more metals to create the future that we want and need. So therefore, it will need to be metal smart. And I strongly believe that extractive metallurgy is the bridge from the resources that we have to clean energy and circular manufacturing and the industries of tomorrow. Thank you very much for your attention. And I hope that this presentation was sufficiently clear and maybe we can have some questions.
Yep. Thanks very much, Aleks. Yeah, that was a very nice presentation to really help us put things in perspective about where we are and where we have to go in the near future to provide these metals for clean energy technologies. Yeah, we have time for questions. So either just unmute yourself or write something in your question in the chat and I'll read it out. I had a question for you, Aleks. So with the battery recycling, you talked about the reduction in nickel and cobalt reducing the value of the black mass. So what's your perspective on LFP then? Is it even more challenging because there's the value is less?
So it is more challenging because the value is less. That's true. I think that cobalt has been the main driver for processing the end-of-life lithium batteries when we first started doing this. And the first batteries were basically a lithium cobalt oxide. But with the limited availability of cobalt and its cost, there was a motivation for the producers to reduce it, and they have been reducing it continuously to the point where these days with the LFP batteries, it's not even there anymore. And that's great for the cost of the battery when it's originally produced, but not good for the recycling businesses, which were hoping to get some return on invested capital, and they're struggling basically. So we've been developing new technologies which are lower cost, that involve reagents that would not be able to recover the cobalt or nickel if they were present there. But for the lithium, they're effective and will help design, develop, operate a commercial plant that recycles those. At the moment, nobody's doing that, however. Everybody is focusing on the beneficiation, recovery of the other components, like the current collectors, steel shells, and then the black mass is sent for recycling elsewhere. I hope that we can see more commercial operations, especially with some of those novel technologies, which maybe can do that effectively commercially.
Yeah, hopefully we can develop that in Australia in the next few years.
Yeah.
Sylvester has a question here. He's a very wonderful presentation. How selective is the recycling system in terms of recovering lithium? Because usually black mass contains various other elements at high concentration of reagent. Most of these metals are soluble and will be leached alongside the lithium. So yeah, maybe you could expand a little bit on that. Yeah.
Yes. So typically the base metals would require acidic systems to effectively solubilize and recover. But lithium doesn't require an acidic system. It can leach effectively in alkaline environment, in some benign reagents. And if there are no cobalt, nickel, copper type elements in the feed, we can focus on the lithium alone. I think that would be the future. Those systems also are relatively tolerant to small amount of base metal impurities because they will not dissolve in the first place. I think that there are several options of progressing this. Some of them involve ionic liquids, which are a great opportunity if we can overcome some of the viscosity issues. Researchers are constantly coming up with new ways. And I think that eventually we will see a wave of material available for processing, which would make it probably more commercially attractive for companies to go ahead with investing in capital.
Thank you. Yep. Any more questions or comments? Go ahead and just unmute yourself or type in some question. So one other question is, you talked about sensors and measurements for smart process control. So of course you'd probably measure pH and temperature. What else do you measure? What else more other things you measuring? Yeah.
I see, George, that the companies producing characterization equipment are offering new tools for online monitoring of mineralogical content of the feed, for example. And that's a great tool to ensure that the dynamic nature of the feed is appropriately accounted for, and changes in the process conditions are made timely so that those variations are not disturbing the process, and perhaps if they're valuable components, they can be effectively extracted, recovered. Yeah. That's one example. I think in my research focus, I've generally steered away from very expensive equipment, but those are opportunities which cannot be ignored. And I think that with the development of AI, there can be better integration of that information with the process control.
Yeah. Sounds good. Thank you. Anyone else? Other question or comments? No, we might as well thank Aleks again. Thank you very much for a nice talk and discussion.
Thank you very much. Thank you very much, colleagues. Thank you, George, for the opportunity.
Yeah. Okay, thanks everyone. See you next time.
Bye-bye.
Bye.